the transistors or the gates in an integrated circuit are connected to each other to form the circuit using metal layers. And any normal CMOS process will have many layers of metal. So what you see here is a picture, is a cross-section view of a CMOS metal stack, what is called a metal stack. In fact, it is a cross-section view of an entire CMOS stack, not just the metal stack. If you look right at the bottom, you'll see the N-well and diffusion. And if you're familiar with MOSFETs, then you will know what those mean. And N-well is the part of the silicon in which PMOS transistors are fabricated, and P-well would be where the NMOS transistors are. So what you see here is an N-well. In the N-well, you see diffusion, which is the source and drain implant. So what you see as diffusion is a source and drain implant, and then you have a polysilicon gate that you can see here in pink. Okay, and so between the polysilicon gate and the silicon substrate is the gate oxide. This particular metal stack is what is used in the SkyWater library. So we have a SkyWater open source standard cell library, which is for a foundry called SkyWater in the US. And the SkyWater technology on which the library is based is what is depicted in this diagram here. So you will see that, for example, the polysilicon gate thickness is 0.18 microns. Okay, and then above the polysilicon is some dielectric of thickness 0.121 microns, and so on. So these are all this polysilicon, the diffusion, all the dielectrics that are associated with the polysilicon gate. All those layers are what is called as front end of line layers. Okay, and sometimes they're called base layers. So the base layers or front end of line layers are the layers that actually are used for the transistors. Then from the diffusion up, we have this metal connectivity, these layers of metal for connection, making connections. The first metal layer is what is called the Li layer that you see here. It's a very thin layer. It's called local interconnect. Li stands for local interconnect. And you can see its thickness is only 0.1 microns. It's a very thin little layer of metal, which is only meant, as the name indicates, for very local interconnects. You don't want to run very long stretches of wire using the Li layer, because the resistance of the Li layer will be very high. Because it's such a thin layer, its resistance will be very high. So it's not used very much for creating nets. It is just used for creating local connectivity between transistors. Okay, and between the local interconnect and the diffusion, you have the Li con layer, which is a contact layer to make connections between the local interconnect and the diffusion layers or the polysilicon layers. You can see that there's an Li con here connecting the local interconnect to the diffusion, and you have an Li con here connecting the local interconnect to the poly. So these are layers that are used for making transistors and just connecting the transistors to each other in a very local area. And that's how you would create, let's say, a standard cell. So the standard cell itself will use local interconnect to connect the transistors. But then when you're connecting the standard cells, so inside the standard cells, the transistors are connected using local interconnect and metal 1, let's say. But the standard cells themselves, when they're connected to create the logic circuit, you do not use the local interconnect for those connections, for those wires. Okay? In fact, most of the time, we don't even use metal 1. We use the other layers, the upper layers of the stack. In this particular technology, we have 5 layers of metal, not counting local interconnects, metal 1 to metal 5. You can see them here. As you go up in the metal stack, the metals get thicker and thicker. Okay, so metal 1 and metal 2 have the same thickness. You can see they're both 0.36 microns. Metal 3 and metal 4 are thicker metal layers. Both have the same thickness. And then metal 5 is a very thick metal layer. Okay, the thicker the metal layer, the less its resistance. But when a metal layer is thick, you cannot create lines that are very close together. Thicker the metal layer, the The wider the metal lines would have to be, and the larger will have to be the space between adjacent metal lines. So there is a trade-off between thickness and density of metal wiring. For very dense metal wiring, you will have to use metal 1 and metal 2, because the pitch of metal 1 and metal 2 will be very less, or the width and the space will be very less. So you can create very dense wiring in metal 1 and metal 2. With metal 3 and metal 4, the density will be less, but the resistance will also be less because they're thicker layers. And metal 5 is a very thick layer. It will have very low density. Usually what we will use metal 5 for is exclusively use it for delivering VDD and ground to all the standard cells. Every standard cell needs VDD and ground. That needs to be delivered to every standard cell through some metal layer. And we will usually use metal 5 exclusively for conveying VDD and ground across the chip. Okay. And then between the layers, between any adjacent pairs of layers, between, let's say, metal 3 and metal 4, you have to have holes through the dielectric. Okay, every layer of metal is separated from every adjacent layer with a dielectric, and through those dielectrics are metal connections to connect to make connections between the different metal layers. And those layers that are used for connecting metal layers are called vias. So you can see here VR1, VR2, VR3, and VR4. VR3 are holes in the dielectric that are filled with metal that connect metal 3 to metal 4. Okay. This particular technology also has metal capacitance layers. So you can see a cap M and a cap 2M. So these are just thin layers of metal that are optionally there. They're not used for creating wires. They're only used for creating capacitance. So if you want to create a capacitance, if you use cap M, you create a capacitor between the cap M layer and the metal 3 layer underneath. You'll create a parallel plate capacitor, let's say. And the cap M layer is connected to metal 4 through VR3, and the metal 3 is connected to metal 4 also through VR3. Okay, so the VR3 is one layer. So this is a standard metal stack. And in this particular case, this metal stack is from the Skywater Foundry. And today, most chips that are designed will have as many as 13 layers of metal. Here you see only 5 layers of metal, but it's very common today to have 9, 11, 13 layers of metal in the technology. And the more layers of metal that you have, obviously the easier it is to create wires, because you have a lot more resources for creating wires when you have more metal layers. But the more the layers of metal that you have, the more expensive the process gets. So it's a cost versus capacity trade-off. You will see that between all the metal layers there are dielectrics. So, and the dielectrics all have certain dielectric constant. So those dielectric constants are mentioned here. They're all around 4, because that is 4 is roughly the dielectric constant of silicon dioxide. And this dielectric constant is important because it determines the capacitance between the metal layers. Every metal layer will have some capacitance. So any wire that you route in metal 1, metal 2, metal 3, metal 4, that wire will have some capacitance depending on which layers of metal are used in creating that wire. And again, recognize that one particular wire or net, remember the word net, and net is just another word for wire. So a net will be built not necessarily using in just one layer of metal. A particular net may run may go through many layers of metal. So you may have a net with pieces of the net will be in metal 2, other pieces in metal 3, and so on. And those pieces of the net will be connected to each other with vias. So that's the way that wires are implemented in a CMOS ASIC. You have to know that there is a metal stack and there are many layers of metal in the metal stack. How many layers of metal there are is defined in the tech left. And when we do automatic routing to create the nets, The thickness is not something that is that the router is actually aware of. The router is only knowing the resistance and capacitance of the particular metal layer.